Your building's grid connection failed at 2:47 p.m. Somewhere on the street, a utility transformer still holds voltage on its primary winding, waiting for repair crews. But your floor is dark. That is not a total blackout, it is a cascade, and where your floor sits inside that cascade decides everything that happens in the next 8 minutes. Subscribe now, because this sequence maps exactly where your apartment lands inside it. Every high-rise runs on a fixed electrical hierarchy. Main disconnect, sub-panels, dedicated circuits, each stage built to protect the next one downstream from fault current. When the grid drops, that hierarchy, not the outage itself, decides who keeps light, who keeps water, and who gets nothing until a utility crew finishes repairs outside on the street. That hierarchy activates the instant the utility transformer de-energizes. At T-0, the primary feed collapses and the main disconnect at your building's service entrance opens automatically, isolating the structure's internal wiring from a dead grid before any fault current can propagate inward through the risers. This is load shedding in its most basic form, the building's protection scheme sacrificing the whole internal network rather than risking equipment damage from an unstable return of power. Within 30 seconds, every sub-panel on every floor loses feed simultaneously. There is no gradual dimming, because distribution boards are engineered to fail cleanly, not slowly. From T30 seconds to roughly T3 minutes, battery-backed emergency lighting activates on its own dedicated circuit, required under ANCOR NFPA 101 Life Safety Code. To sustain illumination for a documented minimum of 90 minutes on stored charge alone, independent of any generator start sequence. That circuit covers lobbies, stairwells, and exit signage only, never apartment units, never HVAC compressors, never your hot water heater. Your unit's outlets stay dark because they were never wired onto that emergency branch. The branch exists strictly for egress, not for comfort or convenience. The branch exists for egress, and 4 floors below your unit, the elevator system is already executing a separate, unrelated protocol of its own. Between T3 minutes and T4 minutes, the elevator controller initiates Phase 1 emergency recall under ANCOR ANSI ASME A17.1, sending every car in the bank directly to the ground floor, holding the doors open, and taking the entire bank offline until stable power, grid or generator, is confirmed by onboard control logic. If a car happens to be between floors when the recall signal fires, it proceeds to the nearest floor in the direction of travel before opening, a fail-safe written directly into the controller's firmware, not left to chance. From T4 minutes to T8 minutes, HVAC air handlers detect 0 supply voltage across their motor windings, and their dampers fail to a closed or last known position depending on actuator design, halting mechanical air circulation across the entire building at once. Floor by floor, warm air stops moving through the ductwork, cold air stops moving through the ductwork, fresh air intake dampers on the rooftop mechanical level close as well, sealing the building's envelope tighter than it runs under normal operation. The building's internal climate now depends entirely on stored thermal mass in the concrete structure, not on any machinery still drawing current from a live panel. The building's internal climate depends on that thermal mass because at T8 minutes onward, the generator, if the building has one installed on site, starts and the automatic transfer switch, or ATS, closes onto the emergency bus, feeding only a pre-selected list of circuits defined at commissioning. Most residents assume that moment restores power to their apartment. It does not, and this is the reveal that separates residents who understand their building's wiring from residents who simply occupy space inside it. ANCOR, Generator Sizing Standards for Commercial High-Rise Document. Typical 20-floor emergency generators sized for approximately 150 to 250 kilowatts of dedicated legal load. Enough to run elevator recall motors, fire alarm control panels, stairwell pressurization fans, and code-required emergency lighting, but only a fraction of the 2 to 4 megawatts of fully occupied 20-floor building draws under normal HVAC and appliance demand. The math itself is the exclusion mechanism, a generator engineered to sustain life safety systems for 72 continuous hours, running on a finite diesel reserve stored on site, cannot also carry 200 apartment units each pulling 230 V single-phase current for refrigerators, water heaters, and air conditioning compressors simultaneously. Some buildings extend generator coverage to domestic water booster pumps as a legal option beyond the minimum code requirement. But that decision is made at the design stage, building by building, and most developers decline it to control installed generator capacity and fuel storage costs, both of which scale directly with contracted kilowatt output. Your unit was never budgeted into that emergency load calculation at any stage of the building's original electrical design. Your unit was never budgeted into that calculation, and where your unit sits vertically changes exactly how that absence gets experienced on the ground floor and every floor above it. Floors 15 through 20 lose usable water pressure first, because the domestic booster pump, now unpowered by the same feed that just failed, can no longer overcome the static head required to push water above the rooftop tank's remaining gravity feed. Those same top floors also drift into thermal instability fastest, since the concrete mass directly above them is thinnest, leaving stairwell emergency lighting as the only illumination source available for the next several hours of darkness. Floors 8 through 14 fare measurably better on both counts. Residual head from the rooftop tank still delivers partial pressure for 20 to 40 minutes after the booster trips offline, and surrounding floor mass above and below slows both heat gain and heat loss simultaneously across that middle band. Floors 1 through 7 retain the strongest water pressure of the three zones, since static head from any elevated tank naturally favors lower elevations by simple physics, though ground-level heat gain through unshaded glazing and street-level security concerns become the dominant variables instead of thermal drift for residents in that band. Drop a comment with your floor number and what you noticed the last time power went out in your specific building. The three-zone pattern holds across nearly every high-rise electrical topology, regardless of city, climate, or construction era. The three-zone pattern holds because concrete itself performs engineering work that predates every electrical system installed inside it. Before automatic transfer switches existed, buildings relied on gravity-fed emergency risers and mechanical interlocks, physical logic instead of firmware logic, to sustain minimum life safety systems during a utility outage, with no relay bank and no digital controller involved anywhere in the chain. That same pre-electronic principle survives today inside the building's thermal mass, whether or not any resident is aware of it. Anchor concrete thermal mass and R-value data shows reinforced concrete's high thermal lag lets a structure's interior temperature drift by only a few degrees across roughly 4 to 6 hours after HVAC shutdown, even while exterior ambient conditions swing faster outside the building envelope. Anchor ASHRAE building thermal standards on time to temperature drift confirm that lag window holds most reliably on mid-building floors, where surrounding mass insulates from above and below at the same time, buffering both directions of heat flow. Older buildings from before widespread central HVAC adoption were designed around this exact lag, with deeper window recesses and thicker exterior walls that modern glass and steel towers often trade away for daylighting, a trade-off invisible until the exact moment the power fails and mechanical cooling disappears. Residents on floors 12 through 18 who understand this window use it deliberately, closing blinds on sun-facing units, shutting off standby heat sources like electronics left in sleep mode, and treating the first 4 hours as engineering stable, rather than panicking during the first 10 minutes of darkness. Treating the first 4 hours as stable requires a sequence, not a guess, and the full sequence takes under 20 minutes to complete correctly from the moment lights go out. In the first 2 minutes, confirm scope. Check whether it is your breaker, your floor, or the entire building by glancing at a neighbor's hallway light before assuming a full grid failure has occurred anywhere beyond your own panel. In the next 3 minutes, locate your unit's sub-panel and identify which breakers feed your dedicated circuits versus which feed shared building risers. This internal map matters more during an active failure than at any other point across the building's entire operating life. And most residents never build it until the first outage forces the question. Within the first 10 minutes, assess water pressure directly at your tap. Floor 18 and floor 3 will diverge noticeably inside that same 10-minute window, and the difference tells you precisely which zone of the cascade your unit currently occupies. By minute 15, Check the nearest emergency lighting fixture in your hallway or stairwell. If stairwell lights are illuminated, but your unit hallway stays dark, the ATS transferred successfully and the failure is isolated to non-emergency branches only, not the whole system. By minute 20, communicate with adjacent floors directly in person or by phone, rather than waiting on a building-wide announcement that may never come. One resident per floor relaying what they observe builds a vertical data network faster than any building management system can generate a formal report. And that network is precisely what separates diagnosis from confusion in the first half hour of any real outage. One data point at a time is how every failure inside this building gets diagnosed instead of guessed at in a dark hallway between neighbors. A 20-floor building losing grid power is never a single event. It is 6 overlapping systems, failing across 6 different timelines, each governed by its own physics, and only one of those 6 systems was ever engineered to reach your apartment directly. The generator was never yours. The elevator recall was never yours. The emergency lighting was never yours. What is yours is the 4 to 6 hour thermal window, the sub-panel map you built in advance, and the floor-by-floor data network you helped create in the first 20 minutes. Society pretends everything is fine. You know better. Subscribe and become harder to disrupt. Urbanalypse, the idea in the chaos, forgotten hacks for modern survival.